Hi everyone, we are back and we are going to do our lecture for our Fourier analysis and continuous Fourier transforms. So Fourier analysis is a really critical tool. It's an analytical tool that I think is very applicable to many different fields. It's extremely important, I think, for engineers to utilize and leverage in order to analyze systems. And there's lots of different things. You can do a whole class on signal analysis, but even this starting point is really going to be critical in order to utilize this when you're doing experiments, analyzing data, and trying to work with systems. And I think this is a great follow-up from your vibrations class where you analyze vibration signals. So hopefully a lot of this is similar to what you've already covered. So excellent. Now, what is the basic idea of Fourier analysis? The whole idea, now most commonly, we're going to go from time to frequency space. So basically, we're going to have a signal in time, and we are going to convert this signal to a frequency space. So frequency or omega, and you'll get some spikes, maybe something like this. But that's the whole idea. So we're going to take a signal in time space and convert it into frequency space, which is frequency, if I'm in cyclical frequency, f is just in units of 1 over seconds. So basically, it's what's called a reciprocal space. You can see here. So reciprocal. Now, if I have a time signal, time can be converted to a reciprocal space, which is frequency space. I can also have a signal that could be just in units of distance, and the reciprocal space would be an inverse meter space. So that's kind of like an idea we'll kind of come back to when we look at some of the examples, but that's the whole idea. I'm converting one space to a reciprocal space. And most of the time, you're going to be dealing with a time signal. And lots of times, we want to look at and we want to analyze and find in my analysis or in my system, what's my lowest frequency, my fundamental frequency, what's the maximum frequency in my kind of signal space or my signal, and then what's the dominant frequency. Dominant frequency is very important. We'll come back to that in a bit. But let's kind of motivate this a little bit. ECG, you've seen those if you watched any of the hospital shows. We kind of know, and this is kind of the idea of you sample and get into time. But you've seen these signals here. It's amazing to me, and it's something that I still never really fully appreciate. But think about, like, you put on the chest of a human being a little, again, like those little, sticky, the little sticky sensors, right? And through, like, the heart beats, and you're able to measure that signal through all of that biological mess. And the signal that is output from a single cell, like the maximum voltage that a cell can produce, is on the order of 100 millivolts, I believe. And through all that, we only get basically this loss, and we're measuring signals that are on the order of millivolts. So it's just, to me, it's unbelievable that we can still actually measure those things. So you get your ECG signal, and then you're going to convert that, and you're going to, find and count, heartbeats. You're going to look at the QPN, all the kind of electrocardiogram analysis. But basically, you're going to convert this signal. If you want to figure out, your cardiac signal, I have to convert it to frequency space. So I'm going to do a Fourier analysis, and you may do some low frequency noise filtration, high band, low pass filter, high pass filter. You probably heard some of those terms. You're going to filter out some of that stuff and focus on, okay, we're going to look only at this kind of cardiac signal here. So this is a very direct, analysis in, in how you perform Fourier transforms. Musical instruments, and so you can see the difference between an unfiltered and a filtered signal. So you can clean up essentially the signal, kind of in a pre-processing step in order to do that. Differences in music instruments, different notes, right? Those different notes will have different frequencies. And we can kind of distinguish between them. So one of the cool things that I love in Mathematica, you can also distinguish between vowel sounds. So bat, beat, boot. So different vowel sounds have different frequency spectrums. In Mathematica, you can actually pull up and see. Let's see if it's going to allow me to play this. some reason. But anyways, I don't think it's allowing me to play here. But what we can see here is this is our frequency spectrum. So this axis is a frequency space, or frequency, and we see when we play different notes. And actually, change it real quick just to make sure. Let's try to make it consistent with the same instrument. So I'm playing different notes on the same instrument, and you see kind of these different spikes, right? Those are indicative of your different notes. You can see it a little bit clearer here when we're just comparing G sharp, A sharp here, and you can see the difference essentially in those values, or you can see it up here with our piano example. So B sharp and G, you see that different frequency. You see it kind of appears in different spots here. Fantastic. So you can use Fourier analysis to distinguish essentially between those musical and instrument notes. I'm a materials person, so XRD, X-ray diffraction, this is a perfect example of basically Fourier analysis. When you're doing Bragg's law, you're basically relating d, a distance, to an inverse angle, theta. So I'm looking at a real space signal, and then I'm going to compare it to a reciprocal or inverse space signal from this, 1 over theta value. So in XRD, you're kind of looking at that kind of graph, right? So we have usually an intensity versus 2 theta. This is, if I'm looking directly at theta, that's an inverse distance space. So that's a reciprocal space. It's basically like a Fourier type analysis. So you can apply this to lots and lots and lots of different systems. So in XRD, you can even use this to, if I have, for example, a family of polymers, there are some distances that are changing essentially within the polymer. So like this intrasegment distance, intersegment distance. If these are consistent between this distance is changing, this distance is changing, this distance is not changing. Neither is this distance. So basically you see these small distances, so large angles are conserved, but these large distances or small angles are changing. And you can kind of see here, for all the polymers, these peaks don't change, but you get some significant shift down and to the left, which means it's increasing in distance, down and to the left, your JFK or, anyways. No one's watched that movie anymore. But we can see essentially those distances that are changing here. And this type of analysis is just a Fourier analysis, or a very similar type of analysis to Fourier analysis. Finally, and actually really important motivation, DNA, this is Rosalind Franklin. Rosalind Franklin was probably the first person to actually photograph DNA, which is basically DNA fiber from a calf thymus, analyzed, was later analyzed by Watson and Crick. Watson and Crick had expertise in and actually knew about Fourier type analysis. So Rosalind Franklin was basically, an X-ray crystallographer. But when Watson and Crick saw this image, and that it was an X-ray diffraction image or an X-ray image, they saw, this is and they had Fourier knowledge. They kind of recognized, in this image, it's an inverse space. So these really dark bands that are very far apart are going to correspond to what? The smallest distance in my system. So that could be the ATGC, basically those distances essentially in that system here. Then you have kind of these angled, right, at some particular angle here, and there's some repeating distance or some characteristic distance between these bands here, but they're basically smaller, so that means inverse, larger. That's essentially your pitch. And there's angle, there's a twist, and with that, you can really confirm your idea that, hey, DNA is this double helix structure. So unfortunately, Rosalind Franklin did not get the credit, although now, and her story is a little bit tragic, she died at the age of 37, but now, essentially, she's credited with a lot of that work, so which is fantastic. But key idea, motivation, we want to be able to look at and measure and basically do Fourier analysis. So next time, we are going to get into time-varying measurements, and we're going to start to calculate those harmonic coefficients. So we'll see you next time. Thanks. Bye.